by Agnes. And it's about private set intersection for unequal set sizes.
Yeah, thank you for the introduction. So my name is Agnes, and I'm going to present joint work between my university, the Technical University of Darmstadt, Aalto University from Finland, and Parilan University, on private set intersection for unequal set sizes, which have mobile applications. So first of all, what is private set intersection? It's a specific case of secure computation. We have two parties who want to compute their intersection in a private way. So in this example, we have Alice and Bob, who want to get to know which are their common friends. Both of them have a contact list, and they want to compute who is their common friend without getting to know anything else than the intersection. So in this scenario, we have around the same number of elements in both sets. However, we can imagine certain scenarios where we have when Alice plays the role of a server, which has a huge database, and Bob is a client who wants to have Alice wants to provide the service to Bob, and he has much smaller number of elements in his set. An example application is a mobile messaging service, for example, WhatsApp, which has a huge database of registered users, and Bob wants to also register and get to know which contacts he can now speak with through WhatsApp. So he wants to compute the intersection between his contact list and the database of WhatsApp and get to know who he can talk with. And in this scenario, we see that it's a significant difference between the size of the two input sets. Another application could be a malware detection service, either on PC or on mobile. There can be a company, there exist such companies that do mobile malware detection and provide the service to the clients to tell which of their applications are malware, so they need to uninstall it. And this can be also an application, because we see the incentive of Bob that he doesn't want to reveal all his applications, and also the malware detection service doesn't want to give away all its knowledge. And so where are we in PSI? What do we have for now? So we have very efficient protocols for the case when we have similar sizes in the input sets. They are based on almost only symmetric key cryptosets, so they are really, really efficient. However, they require to send data which is proportional to the size of the larger input set as well, for every element of the client in this scenario. So it doesn't really fit our needs, because it's gonna be very inefficient for this scenario. So what else do we have? We also have some linear protocols that are linear in both the set sizes. So we just, but the problem with these protocols is that in general they perform worse than the OT-based protocols, but because they are based on public key crypto. So the research kind of stopped in this direction at some point and went towards the other one. However, they perform much better in this particular scenario when we want to have unequal set sizes. So which protocols that are linear we can adopt to our scenario. And we see that except one of them, where the client needs to perform too much computation, so nonlinear computation, we will be able to adopt all of these to our unequal set sizes scenario. So the first contribution that we have is that we improve these protocols, or these 4 protocols, and adopt them to this particular scenario. So first of all, instead of looking at the protocol in one, we look at 3 phases of the protocol and we shift everything upwards. So we have a base phase where we compute everything that's independent on both the sets. So keys and random numbers and so on. Then we have a setup phase, which depends only on the elements in the database. And we have an online phase, which is efficient, and it only depends on the elements in the smaller set of the client. So what's the point in doing this? The base phase can be pre-computed by the two parties, like for example, when installing the application, so we don't need to know anything about the inputs at this stage yet. The setup phase can also, so we will see that it can, so most of the computation that needs to be done in the setup phase can be pre-computed by the server in advance. So that's another advantage why we separate the setup phase from the online phase. If we are lucky, we might even be able to do the same computation for our clients. And in the online phase, we only do very fast computation on the small set of the client. So to reduce the communication and the storage that's required by both parties, but by the client who has restricted resources, we use Bloom filter to store the database in a more efficient way. So Bloom filters are used for membership testing in the following way. So firstly, we initialize a large array of zeros, of 0 bits. And we have a couple of hash functions. Both parties have knowledge about these hash functions. They agree on it in advance. And when inserting an element like a phone number, we first need to hash the element with all the hash functions, which define a position in this array, and we will set this bit to 1. And membership testing works works the same, because we just need to, receiving an element, we need to hash it with the known hash functions and see if those bits are 1 or 0. And if they are all 1, with a small false positive probability, we can say, okay, the element is in the database. Of course, we will not ever insert plain text elements in this Bloom filter, because that would be insecure. So we first encrypt it and then insert it in the Bloom filter. I just want to point out that we never insert clear text elements in the Bloom filter. And the false positive rate can be controlled by making this array larger. So if we want smaller false positive rates, then we will have a larger array. But it's a much better way to store the database than just storing it encrypted. Okay, and we can also do updates in this Bloom filter by either sending the encryption of the element or the positions that need to be updated. And so it depends on the parameters, which is the more efficient solution. So depending on our scenario, how big our set is and so on, we need to see which of those is the more efficient, and we need to do the updates depending on that. And if we want to allow for deletion, we need to use counting Bloom filters. The only difference is that we have small counters instead of bits in the array, and then we can decrease these counters also if an element needs to be deleted. So just to have a high-level overview on how these protocols work. So the ones that are based on, there are the ones that are based on oblivious pseudorandom function evaluation. There are 3 variants of this. One based on RSA, blind signatures, one based on so-called Nauer-Reingold pseudorandom function, and one based on a garbled circuit evaluation of AES. So it's an AES-based protocol. And so the high-level overview, we have a base phase where we just do pre-computation that doesn't depend on the data. We agree on the keys, on the parameters, and do some pre-computation. And then in the setup phase, the server will encrypt all its database and insert it in the Bloom filter, sends the Bloom filter over to the client, who then stores this Bloom filter. And in the online phase, the client will be able to request the encryption of his elements in an oblivious way. So the server will not know what he's encrypting, and send back the encryption, which can be then unblinded by the client, and he will know the encryption of the element and can check locally if it's in the Bloom filter or not. So he will be able to verify if the element is in the intersection or not locally. And then there's another solution based on Diffie-Hellman. it's the general Diffie-Hellman way. There are two keys generated by the server and the client in the base phase. Then the server will encrypt the database with his key, send it over to the client, who will also encrypt all the elements and then insert it in the Bloom filter. So we see here the communication is much more than in the previous solution, because there we were only sending the Bloom filter. But in some cases, we might allow this for more efficiency. In the online phase, what happens is that the client will encrypt his element, send it to the server, who also encrypts it with his key, and then send it back. And so the client can check if the element is in the intersection in the same way as before. Okay, so we also implemented all these protocols to see which perform better in which scenarios, and like a prototype implementation, both in mobile setting and if we have two PCs that want to perform this. So let's first look at the scenario where we have two PCs. So we implemented these protocols in C, C++. We were lucky because we could use the hardware accelerated version of AES for the last protocol. So both for encrypting the database and for the garbled circuit evaluation there. Whoever knows what that means. And so here we look at the scenario. So I put some numbers which match the scenario of malware detection. So we have a couple of millions of elements in the database, like 120 elements in the client set. And we can see here that the best runtime we can get is with the AES-based protocol. However, it requires the most communication and storage in the base phase, because the client needs to store some garbled circuits, and that makes it less efficient, and in some scenarios that might be prohibitive, so we need to go for a less runtime efficient solution in that case, and we can go for Navarine called PSI, for example. If we don't have ASNI, then this solution is out of the question, so it becomes way less efficient than all the others. And if we have, so we implemented it in Android and with Java, and there we couldn't use ASNI. Also, the elliptic curve crypto version of the Diffie-Hellman protocol became less efficient because that was also not better. The finite field version was better on the mobile than the elliptic curve version. And so we see that here the best solution, so with the same numbers here, the best solution would probably be the RSA-based PSI protocol. And then if we look at a bigger, like a much larger scenario with more than 1 billion users in the database for a messaging service and a bit more elements in the client set as well, then we see that this becomes inefficient. So we're not too happy to perform days of computation in the setup phase. And so those days go for encrypting the database, so the billions of elements. And can we do anything about that? So what we have seen is that we can use the same encrypted database for multiple clients, and then we can assume that the service provider will be able to encrypt the database, do this couple of days computation at some point, and then just use this encrypted database inserted already in the Bloom filter and send it either in a content delivery network or so just send it to all the clients, the same encrypted database. And this helps us save, in most of the cases, except for the Diffie-Hellman case, it helps us to save all these days of computation, or just a couple of hours. So for Diffie-Hellman, we don't save it because the client also participates in encrypting the database, so we can kind of cross this solution out. And then we see that there's still a problem, which is that we need to store around 5 gigabytes of data in the client side. So the communication would maybe be okay, but we also need to store this 5 gigabytes of data in the mobile. So that's not that practical yet. So there's another work that just came up 1 or 2 weeks ago, which uses cuckoo filter instead of Bloom filters. So they managed to go down to around 4 gigabytes instead of 5.4. So that gives us some hope. Maybe it can get better for this scenario as well. But so here the best would be to use RSA PSI in any case if we are allowed to store this amount of data, because that's the most efficient solution. So in summary, we have studied all these protocols. We wanted to see if there's a generic best solution in this scenario, but we've seen that it depends on the parameters, which scenario is the most efficient for our particular application. And we extended with a couple of new ideas also. So thank you for your attention. I'm happy to answer questions.